Hi, greetings everyone, and welcome to this new video lecture on fascinating topic engineering noise and its control. This video lecture marks the beginning of our Unit 4, where we will delve into fundamental principles of understanding sound and its measurements. As you can see on the slide, it is a part of the course ME22088 Vibration and Noise Control. It is myself, Dr. C. Sannamarikannan, Associate Professor in the Department of Mechanical Engineering at SVC. I am excited to guide you through this important unit. This slide provides a visual overview of the interconnected aspects what we are going to explore within the broader field of noise. You will notice the diagram illustrating the relationship between acoustics, noise, control engineering, and policies. Understanding how these areas intersect is crucial in effectively addressing and mitigating the noise issues. So let's embark on this journey to unravel the intricacies of sound and how we measure it, which forms the bedrock for effective noise control strategies. As such, we have a foundational understanding of broader context of noise control. Let's zoom in on very essence of what we are dealing, sound itself. Here we are focusing on understanding the sound waves and we are breaking down into some crucial concepts. Let me see the definition of sound. We see that sound is fundamentally a mechanical wave. This means it requires a medium such as air, water, or solids to propagate or travel. Think of it like ripples in a pond. They need the water to spread out. Sound energy is transmitted through these mediums as a wave. Next, our focus is on source of sound. We learn that the sound waves are generated by vibrating sources, whether it is a loudspeaker moving back and forth or a musical instrument string oscillating, even the movement of air creating speeches. Vibrations are the initial cause. These vibrations create pressure variations in the surrounding medium, and these variations are what we preserve as sound. The next important thing is propagation mechanism. The transmission of sound isn't about entire medium moving from the source to our ears. Instead, it involves the oscillation of particles within the medium. These particles bump into their neighbors, transferring energy through pressure variations. Imagine a chain reaction where each link moves slightly, passing through the motion along without entire chain which is moving. Finally, we are having the fourth important thing, perception of sound. Ultimately, we perceive sound when this pressure wave reach our ears. Our ear acts as a transducer, converting this mechanical wave into signals that our brain can intercept as a sound. So, from the initial vibration to the final interpretation in our brain, it is fascinating chain of events. Understanding these fundamental concepts, the definition, source propagation, and perception of sound is crucial as we delve deeper into measurement and control in the subsequent part of this lecture. Building upon our understanding of sound waves, let's now focus on a crucial concept when characterizing a sound wave, that is, sound power. Here we are understanding the sound power through this slide, which is highlighting four important aspects of this quantity. Firstly, as indicated by the musical note icon, sound power is the total energy radiated by a sound source per unit time. Think of it as the inherent strength or output of the sound source itself. It tells us how much acoustic energy the sound is emitting. Secondly, it is depicted the measurement microphone icon. The measurement unit for sound power is watt. Just like we measure the power of a light bulb in watt, we use the same unit to quantify the energy output of a sound source. So when you see a sound power level expressed, it will ultimately relate back to this fundamental unit of energy per unit time. Third, it is very important distinction. Sound power is an intrinsic property of the source as illustrated by the sound wave icon with the X indicating independence. The sound power of source remains unaffected by environmental factors or the distance from the sound. Whether you are close to a loudspeaker or away in a quiet room, the loudspeaker sound power output remains the same, assuming its operation doesn't change. Finally, to provide a practical example, consider loudspeaker wattage. While not exactly the same thing technically, the wattage rating of a loudspeaker is a good indicator of its capability to produce sound, and thus it is sound power. Higher wattage generally implies a greater capacity to radiate the acoustic energy. Understanding sound power is essential because it allows us to characterize the fundamental strength of a noise source independent of the environment in which it operates. This forms a crucial basis for comparing different noise sources and for designing effective noise control measures. Let's shift our focus from the power of a sound source to how the power is distributed and perceived at a certain location. This brings us to the concept of sound intensity. Here, this slide I am going to present is understanding the sound intensity, breakdown into what it means and what influences. Starting with the definition of sound intensity, here we see that it defined as the power per unit area. Essentially, it tells us how much sound energy is passing through a specific area, oriented perpendicular to the direction of the sound wave. The unit for sound intensity is watt per square meter. Think of it as a concentration of sound power at a particular point in space. Moving to the section on key factors influencing the intensity, we find that sound intensity is primarily influenced by two main factors: power of the sound source, what we just discussed, and distance from the source. Understanding how these factors interact is critical for predicting how loud a sound will be at different locations. The section on the impact of distance on intensity elaborates on this relationship. As we move further away from a sound source, the intensity of the sound decreases. This is because the sound energy is spreading out over a larger and larger area. This relationship can be quantified by the formula I equal to P divided by 4 pi r square for a point source, which we see in this formula. This formula clearly illustrates that the intensity I is inversely proportional to the square of the distance r from the source. This means that even a small increase in distance can lead to a significant drop in sound intensity. Imagine the sound waves radiating outwards like an expanding sphere. The same amount of energy is spread over a larger surface area as the radius of the sphere increases. In summary, while sound power is the inherent strength of the source, sound intensity describes how that power is distributed in space and what we ultimately perceive in terms of loudness at a specific location. Understanding this relationship between sound power, distance, and sound intensity is fundamental to addressing noise problem effectively.
While sound power describes source output and sound intensity describes power distribution, sound pressure is what our actually detect. Here we are going to see understanding the sound pressure. The main important thing is sound pressure is the local pressure deviation. Sound waves can cause tiny fluctuations in the ambient atmospheric pressure. These variations, this minute increases and decreases in pressure that our eardrums respond to, allowing us to perceive the sound. The next important thing is sound pressure is measured in terms of pascals. The pascal is the standard unit for pressure and it quantifies the force exerted by the sound wave on a given area in the atmosphere. So when we talk about how loud a sound is in scientific terms, we are often referring to it as sound pressure level, which is ultimately based on this Pascal unit. The next point is intensity relationship. Sound pressure and sound intensity are related particularly in a free field and environment without reflections. Formula I equal to P into C into P RMS square shows this connection where I is intensity, P RMS is root mean square of sound pressure, P is the density of the medium, C is the speech sound in that medium. This equation underscores the higher sound pressure corresponds to higher sound intensity. Finally, point number 4 emphasizes sound pressure is the most commonly measured quantity in acoustics, while sound power is fundamental to the source and intensity describe its distribution. Sound pressure is what we can directly measure using the microphones. These measurements then provide valuable insight into the characteristics of sound waves and which are the basis for many noise assessment and control strategies. In essence, sound pressure is the manifestation of sound waves that directly interact with our hearing. Understanding this definition, measurement and relationship with sound intensity is key to practically assessing and managing noise in various environments. So far, we have discussed the overall characteristic of sound in terms of power, intensity and pressure. Now, let's delve into the frequency content of sound, which is crucial for a more detailed understanding and analysis. In this slide, I am introducing the concept sound spectra. The first key aspect highlighted in this is the frequency content of sound. Most real world sound aren't composed of a single frequency, but rather a combination of many different frequencies occurring simultaneously. The sound spectrum is a way of representing this frequency content, essentially showing us which frequency are present in a sound and their relative contribution to the overall sound profile. Think of it like breaking down a musical chord into individual notes. Next, we move to this red box, which is amplitude representation. Sound spectrum doesn't just tell us what frequencies are present. It shows us the amplitude of each of these frequency components. The amplitude in the frequency domain corresponds to the level or loudness of each individual frequency within the sound. Higher amplitude at a specific frequency means that frequency component is more prominent in the overall sound. Next, the blue box introduces the Fourier analysis methodology. How do we actually obtain this sound spectra? The answer lies in a powerful mathematical technique called Fourier analysis. This technique allows us to transform a sound signal, which is typically represented in the time domain, which will then converted into frequency domain via the time domain. How the sound pressure changes over the period of time, revealing its constant frequencies and amplitudes. It's like taking a snapshot of sound and dissecting it into its fundamental frequency components. Finally, the dark teal box discusses types of spectra. Sound spectra can be broadly categorized. Line spectra are characteristics of sounds with discrete frequencies like pure tone or musical instruments playing single notes. Continuous spectra on the other hand represent sounds that contain broad range of frequencies such as white noise or the sound of rushing water. Understanding the type of spectrum helps us analyze the nature of the sound. In essence, analyzing the sound spectrum provides a much richer understanding of a sound than just looking at its overall pressure or intensity. It allows us to identify the specific frequencies that contribute to the sound and their relative strength, which is vital for tasks like noise source identification, acoustic design, and the development of targeted noise over control measures. Now we have a grasp of sound pressure and intensity. We need a practical way to quantify and work with these values, especially considering the vast range of sound pressures and intensities we encounter in the real world. This brings us to the crucial concept of decibel scale. Here we are going to see the decibel scale, which I am going to highlight the key reason why we use this logarithmic scale in acoustics. The first reason is shown in the dark blue box is that decibel scale is a logarithmic scale. Sound pressure and intensity can vary by many orders of magnitude from the faintest whisper to the roar of a jet engine. A logarithmic scale effectively compresses this vast range into a more manageable set of numbers, making it easier to work with and interpret. The next thing, the red box. We see that decibel scale offer easier use by compressing enormous range of sound pressure into a scale typically spanning from 0 dB to 140 dB for practical hearing level measurements. It simplifies communication and the measurement process in many world applications. Main thing is we have to imagine that trying to discuss sound level using Pascals directly, then the numbers would be incredibly large or small and cumbersome. The next box that is the light blue box, explains the connection to our perception of loudness. Interestingly, our human perception of loudness is also approximately logarithmic. A tenfold increase in sound intensity doesn't sound 10 times louder to us. It sounds roughly twice as loud. The decibel scale mirror this logarithmic perception, providing a more intuitive measure of how we experience sound intensity in reality. Finally, this dark teal box highlights simplified calculations. Working with logarithmic scale transforms multiplication and division operation into simpler addition and subtraction. This significant advantage when dealing with combination of sound sources or the effect of distance and barriers on sound levels, making calculations much more manageable. In summary, decibel scale is not just an arbitrary unit. It is a powerful tool that allows us to effectively manage the wide range of sound pressures and intensities, align with our perception of loudness, and simplifies acoustic calculations. It is a fundamental concept that we will use extensively as we delve further into noise measurement and control. We understand the decibel scale advantages. Let's apply it to the concept of sound power. Here, this slide focuses on understanding the sound power levels and how we express the inherent strength of a sound source using decibels. Starting with this first thing, that is the formula for sound power level, that because sound power itself is often very small in number, we use the decibel scale to express it in more practical way. The sound power level denoted as L suffix W, which is equal to 10 log 10 of P suffix 0, that is reference sound power, then P itself, that is sound power source. Then the next thing is reference sound power. This is a standardized value of 10 to 12 watts, that is 10 to the power of minus 12 watts. This very small value serves as a common baseline for comparison. By using this reference, we can express the sound power of different sources on a relatively decibel scale. This allows us to easily compare the power output of various machines. Finally, decibel scale representation. Essentially, the sound power level in decibel is a logarithmic scale that expresses the ratio of the sound power output of a source in comparison to this fixed reference power level. This provides a clearer and more manageable understanding of the sound intensity produced by the source independent of the environment. Think of sound power level as the acoustic horsepower of a sound source. Its fundamental characteristics that tell us how much sound energy the source is inherently capable of radiating, expressed in a way that convenient to use thanks to the decibel scale and the standardized reference power. Now, just as we expressed sound power on a decibel scale, we do the same for sound intensity. In this slide, we are going to see understanding the sound intensity level, which guide us through how to quantify sound intensity using the decibel scale. We will be covering several key aspects as shown in this segment of the diagram. We will start by understanding the fundamental concept of sound intensity level itself. Then we will look at the crucial reference intensity I0 used for this scale. Following that, we will examine the decibel scale formula specifically for sound intensity level. We will also touch upon logarithmic nature of decibels. Finally, we will brief discuss some important application of sound intensity measurement. So let's begin by exploring how we use the decibel scale to express the intensity of sound we experience. Most important practical measurement is sound pressure level. So in this slide, I am going to discuss you understanding the sound pressure level and explaining how we can express the sound pressure we measure using the decibel scale. The first point is sound pressure level itself, denoting as L suffix P. Since sound pressure also span a vast range, we use the decibel scale to express them in a more manageable way. The sound pressure level, denoted as L suffix P, is calculated using the formula 20 log of 10 P suffix O, P root mean square value. Notice that we use a factor 20 here as sound pressure is related to sound intensity by a square law. The next point here is root mean square pressure. When we measure fluctuating sound pressures, we typically use root mean square value. This P, root mean square value, represents effective sound pressure, providing a single value that related to the energy carried by the sound wave. It is crucial for calculating both sound intensity and sound pressure level. The next point defines the reference sound pressure. Just like sound power and intensity, we need a reference point. Standard reference source point is P naught, that is sound pressure P naught in air is defined as 20 micropascals. This value is significant because it is approximately the threshold of hearing for humans at a frequency of 1 kHz. It serves as our baseline for measuring and expressing sound pressure levels. Finally, the next and last point reiterates that decibel scale, it is the logarithmic unit used to measure sound pressure level as well as sound intensity level. This logarithmic scale allows us for easier comparison and understanding of the wide range of sound levels we encounter, relating more closely to our perception of loudness. Therefore, when you see sound level reported in decibels, they are most often referring to sound pressure levels, reference to that crucial value of 20 micropascals. This is the standard way we quantify and communicate the loudness of sound in acoustics. In real world scenario, we often encounter multiple sound sources contributing to the overall noise level. Since decibels are logarithmic unit, we can't simply add them arithmetically. This slide combining sound level effectively, providing us with the tool and rule of thumb for accurately determining combined sound level from multiple sources. The first point is total sound level formula. For most accurate calculation of the combined sound level L suffix total from two sources with level L1 and L2, we use the formula that is L total equal to 10 log of 10 within bracket 10 L1 divided by 10 plus 10 L2 divided by 10, the bracket closing, which is measured in decibel. This formula accounts for the logarithmic nature of the decibel scale and allows us to correctly combine sound level from different sources. While this formula is precise, we often use simpler approximations in certain situations. Point number 2 gives us a useful rule of thumb for same levels. When we have two sound sources producing the same sound level, the combined sound level increases by 3 dB. For example, if one machine produces 80 decibel and another identical machine also produces 80 decibel, the combined level will be approximately 83 decibel only. This rule is handy when dealing with multiple identical noise sources. The next point here is impact of 10 decibel difference. If there is significant difference of 10 decibels or more between two sound sources, the higher level dominates and the combined sound level will be approximately equal to the higher level plus only 0.5 dB. In practical terms, quieter source contributes very little to the overall sound level when there is such a large difference. Finally, point number 4 is example of combined levels. It reiterates the rule for thumb for same levels. If two machines each produce 80 decibels when combined, they result in a total sound level of 83 decibels. This illustrates the nonlinear way in which decibel levels combine. Understanding these principles is crucial for assessing the cumulative impact of multiple noise sources in various environments and for designing effective noise control strategies that target the most significant contributors.
In many practical situations, we might measure the combined sound level of multiple sources, but we need to determine sound level of a specific source within the mix. Here in this slide, isolating the sound level is explained, which outlines the process considerations for extracting the individual sound level of a source from a combined measurement. Next, the important thing we are seeing by point. This segment introduces the concept of finding individual sound levels. The process is crucial in sound engineering and acoustics for identifying the noise contribution of specific machines or sources when a combined measurement is taken. It allows us to understand individual impact of each component. The red segments highlights the need for conversion to linear units because the logarithmic nature of decibels to accurately isolate sound levels mathematically. It is necessary to convert the decibel values back to the linear intensity or pressure ratios. Performing arithmetic operations directly on decibel values will lead to incorrect results. This conceptual understanding is vital for accurate calculations. The next segment represents complex sound level formula. To isolate sound level of one source, that is L1, we know that the combined level L total and the level of another source L2. We can use rearranged version of this combination formula specifically to find L1 if we know the L total and L2. we would rearrange the principles. However, in this slide, I am providing you the formula which is taken from the reference source. If L is L total and L1 are known, the L2 can be given in this way, especially when L total is going to be greater than L1. This formula mathematically demonstrates how to subtract the contribution of one source from the total to find the other. Finally, the last segment gives us a practical example in sound measurement. Let's say we measure a combined sound level of 90 decibel from a machine and background noise together. If we know the background noise level is 85 decibel, we can use the principle discussed implicitly using the inverse of the combination formula to estimate the machine sound level to be approximately 88.3 decibel. This example illustrates the practical application of isolating sound level in real world measurements. Understanding how to isolate sound level is essential for noise source identification, troubleshooting noise problems, and ensuring compliance with noise regulations that often target specific sources within a larger sound space. In many situations, we need to determine the average sound level over a period of time or across multiple measurements. However, due to the logarithmic nature of the decibel scale, simply averaging dB values directly will lead to incorrect result. This slide, I am going to present that calculating average sound level, which outline the correct procedure to be followed. The first thing, empathetically state that direct averaging of dB value is incorrect. It is crucial to remember that the decibel scale is not linear. So a simple arithmetic mean of dB value doesn't represent true average sound energy. The next one below that provides a practical examples of average. It illustrates that averaging 70 dB and 80 dB doesn't give 75 dB. The correct average is approximately 76 dB, highlighting the error in direct decibel average. To get the correct average sound level, we need to follow a specific procedure starting with this one. Convert decibel to linear values. The first step is to convert each decibel value back to its corresponding linear value using the formula 10 times the decibel divided by 10. This essentially reverses the logarithmic transformation. The next, as shown in this box, we calculate the arithmetic mean. Once we have the linear values, we can find their average by simply adding them up and dividing by the number of values, just like a regular arithmetic mean. This average now represents the average sound energy in linear terms. Finally, the last thing is convert the mean to decibel. To express the average sound level in familiar decibel unit, we have to convert linear mean value to decibel using the formula 10 times of logarithmic base difference of 10, that is mean of linear values. Therefore, to accurately calculate the average sound level, we must always convert the decibel values to their linear equivalents. Calculate the arithmetic mean of these linear values and then convert the resulting mean back to decibels. This multi-step process ensures we account for the logarithmic nature of the decibel scale and obtain a meaningful representation of the average sound level. We have discussed the objective measures of sound, power, intensity, and pressures, that is, sound pressure. We quantify them using the decibel scale. Now let's turn our attention to subjective experience of sound loudness. This slide I am presenting you understanding the loudness perception, which highlights several factors that influence how we as humans perceive the volume of a sound. The first thing here I am emphasizing the loudness is the subjective perception of sound. Unlike sound intensity or pressure, which are physical quantities that can be objectively measured, loudness is how our brain interprets these physical properties based on a variety of factors. What one person perceives as loud, another might perceive differently. The second point discusses the influences of sound intensity. While subjective, our perception of loudness is certainly related to the objective intensity or pressure level of the sound. Generally, sound intensity or pressure level do lead to a perception of increased loudness in our auditory system. A louder sound source typically has a higher sound intensity. However, the third point introduces a crucial factor: frequency impact on loudness. Our ears are not equally sensitive to all frequencies. For the same sound intensity level, we tend to perceive mid-frequency sounds as louder than sounds at very low or very high frequencies. This frequency sensitivity significantly affects our overall loudness perception. For example, a low frequency rumble and a mid frequency tone might have the same sound intensity level, but the mid frequency tone will likely be perceived as louder. Finally, the fourth point highlights the effect of sound duration. The length of time a sound lasts can also influence our perception of loudness, especially for very short sounds or impulsive noises. A very brief, intense sound might not be perceived as loud as a slightly less intense sound that lasts longer. The integration of sound energy over time in our auditory system plays a role here. In summary, while sound intensity and pressure are key physical properties of sound, our perception of loudness is a complex phenomenon influenced not only by these objective measures but also significantly by the frequency content and duration of the sound, as well as individual differences in hearing. Understanding these factors is crucial when assessing the impact of noise on humans. Building on our understanding of loudness perception and the fact that our ears aren't equally sensitive to all frequencies. In this slide, I am explaining you hearing sensitivity. I am introducing the concept frequency weighing used in sound level measurements. These weighing networks are electronic filters incorporated into sound level meters to better reflect how humans perceive sound at different frequencies and levels. The first point sets the stage by explaining that electronic filters in sound level meters are used to adjust for human hearing sensitivity, ensuring more perceptually relevant sound measurements. The next point, introducing A weighing, B, that is decibel of A. This is perhaps the most commonly used weighing factor, particularly for measuring moderate levels of environmental noise. The A weighing filter attenuates low and high frequencies, mimicking the sensitivity of the human ear at moderate sound pressure levels. Measurements taken with A weighing are denoted as dB, that is decibel of A. The third point here is B weighing method. Less common than A weighing method, B weighing method provides a different frequency response, and it is sometimes used for higher sound levels. It has less attenuation of low frequencies compared to A weighing. Measurements are denoted as dB, that is decibel of B. The next fourth point is decibel level of C. Designed for high level, low frequency noise measurement, C weighing has relatively flat frequency response across much of the audible spectrum with only slight attenuation at the very low and high ends. It often used in industrial and soundproofing applications where low frequency noise is significant. Measurements are denoted as decibel level of C. The next point is weighing D, that is decibel level of D, specifically tailored for measuring aircraft noise. D weighing account for frequencies that are particularly pertinent to our perception of aviation sounds. Final, the point number 6 explain Z weighing, that is decibel level of Z. Unlike other weighings, Z weighing offers a linear frequency response with no adjustment. It measures the actual sound pressure level across the frequency spectrum without trying to mimic human hearing. This is useful for precise analysis of sound signal itself. In essence, these frequency weighings are crucial tools in acoustics by filtering measured sound signal to approximate the frequency sensitivity of the human ear under different conditions. We can obtain sound level measurements that are more meaningful in terms of potential annoyance or hearing risk. A weighing is a general purpose filter, while others are used for specific types of noise or measurement context. In many world scenarios, sound levels aren't constant, they fluctuate over a period of time. To quantify this fluctuating noise in a meaningful way, we use a metric called L, that is loudness equivalent, otherwise equivalent continuous sound level. So here we are going to understand this L equivalent in sound measurement. The first point here is L equivalent is the average sound energy. That is, L equivalent is a single decibel value that represents total sound energy of a fluctuating sound over a specified period. It is a way to condense a complex varying sound level into single number that is crucial for accurate noise assessment. The second point is that loudness equivalent in terms of constant sound level. Conceptually, loudness equivalent is the level of the constant steady state sound that would have same total sound energy as the actual fluctuating sound over the same measurement duration. This allows us to compare fluctuating noises to steady sounds and aids in noise evaluation. Here, this presents the third point, formula for loudness equivalent. The mathematical definition of loudness equivalent over a period of time t is given by this formula. I am highlighting that. This formula essentially averages the squared sound pressure level, which is proportional to sound energy over a measurement time and then convert back to a decibel level. Finally, I am highlighting the application of loudness equivalent. Loudness equivalent is widely used in both environmental and occupational noise assessments. It is a key metric for evaluating long-term sound pressure and its potential effects on human health and well-being. For instance, it is used to assess noise levels near roadways, airports, and in workplaces to determine compliance with noise regulations and to estimate potential hearing damage risk. In summary, loudness equivalent provides a valuable tool for simplifying the analysis of time varying noise by representing the equivalent continuous sound energy level. It is a fundamental metric in acoustics for characterizing noise exposure over a specific duration. We have explored basic of sound as a wave, how its power and intensity are generated and spread, and how sound pressure is what actually we measure. We learn that the decibel scale is essential for handling the wide range of sound levels and align better with our hearing. When combining or averaging sound levels, simple arithmetic doesn't work. We need special methods due to decibel scale nature. Finally, we touched on our perception of loudness is subjective and influenced by factors like frequency, leading to the use of weighted measurements and the concept of loudness equivalent for fluctuating noise. Thank you for all your attention, and I'm concluding this lecture on understanding sound and its measurement.